If you could stand on Earth and look out across the horizon 250 million years ago, almost nothing would feel familiar. There would be no Atlantic Ocean, no separate continents, no North America drifting away from Europe, no South America pulling apart from Africa, no India racing toward Asia, no Antarctica isolated in a ring of ice. Instead, nearly all the land on the planet would be fused into one colossal supercontinent. One landmass so enormous it changed the climate of the entire world. One terrain so extreme it created deserts larger than anything alive today has ever seen. One interior so dry, so isolated from the sea, that vast regions of Earth may have felt almost alien, even by prehistoric standards. And the strangest part is this: that world was real. Before the continents were broken into the map we know today, before the modern oceans opened, before mammals ruled the surface, Earth spent part of its history in a configuration so radically different that it almost feels impossible to imagine. But it happened. And the evidence is still all around us, locked in mountain chains, buried in rock layers, encoded in fossils, and written into the very shape of the seafloor. This was the age of Pangaea. And if you could walk across it, you wouldn't just be walking across a different planet in appearance. You'd be walking through a version of Earth that behaved differently. The winds moved differently. The rains fell differently. The coastlines stretched farther than the eye could follow. The seasons in some places were brutal. Entire ecosystems lived and died in climates that no longer exist. And somewhere inside that giant world, the foundations of the modern planet were already beginning to crack. Because Pangaea wasn't just a lost continent. It was a temporary arrangement in a restless machine. And when it broke apart, it didn't just rearrange the map, it rewrote the future of life itself. To understand what Earth was like when all the continents were one, you have to do something the human brain is not naturally good at. You have to stop thinking of the continents as permanent. You have to stop seeing coastlines as fixed. You have to forget the modern globe long enough to realize that the planet under our feet is not stable land with some occasional earthquakes on top of it. It is a moving shell. The world we live on is fragmented into enormous slabs of rock called tectonic plates. And those plates are always moving, even if they do it slowly enough to feel invisible in a human lifetime. Continents drift, oceans open and close, mountains rise and collapse. Entire climates are born from collisions that take tens of millions of years. From our perspective, Earth looks finished. From the planet's perspective, it is still under construction. Pangaea was one of the most dramatic stages in that construction. Its name means all Earth, and for a period stretching from the late Paleozoic into the early Mesozoic, it was exactly that, a giant merger of almost all the major landmasses on the planet. Not a perfect single block in the way children imagine puzzle pieces, pressed flat together, but a truly enormous continental assembly, surrounded by a vast global ocean called Pangaea, and bordered internally by smaller seas and basins that came and went over time. Imagine today's continents peeled off the globe and shoved together until the seams lock. South America pressed into Africa, North America welded to Europe and northwestern Africa, Antarctica and Australia tucked farther south. India, not yet a wandering bullet, but part of a much larger southern arrangement. What emerges is not just a supercontinent, it is a world with a completely different logic. Because continents do more than carry forests, mountains, and cities. They control the atmosphere. They steer ocean currents. They shape where rain falls, where deserts expand, where glaciers survive, and where evolution has room to experiment. And when you combine nearly all the land on Earth into one giant mass, the consequences become extreme. One of the first things you would notice on Pangaea is scale. Modern continents already feel huge to us because we experience them in fragments. We cross them by plane. We see them through maps and borders. But Pangaea was not simply big in a modern sense. It was geologically oversized. It stretched across a massive portion of the globe and created interior regions so far from the sea that they likely experienced conditions few places on Earth experience today. The ocean is one of the greatest climate stabilizers on the planet. Water stores heat, releases it slowly, transports energy through currents, and pumps moisture into the air. Coastal regions tend to be moderated by that influence. Temperatures swing less violently. Rain is more accessible. Weather is buffered. But move deep enough inland, far away from maritime influence, and the planet becomes harsher. Now imagine inland, not as a few hundred kilometers. Imagine inland as a continental interior so vast that in some regions, the nearest major coastline might have been unimaginably distant. That is one of the defining features of Pangaea. Much of its interior was likely dry, highly seasonal, and climatically severe. Huge deserts appear in the rock record. Ancient dune systems, the size of countries, once shifted under winds that crossed open continental interiors for extraordinary distances. In places, the landscape may have resembled a fusion of the Sahara, Central Australia, and the American Southwest, but stretched across a prehistoric world with stranger skies, different vegetation, and animals unlike anything alive now. This is where the image of Pangaea becomes truly unsettling. Because most people picture the ancient Earth as one giant green jungle, filled with dinosaurs. That image is wrong in almost every way. For one thing, when Pangaea was at its peak, dinosaurs had not yet become the dominant rulers people associate with prehistoric Earth. In fact, much of the story of Pangaea belongs to a world before the classic dinosaur age fully took over. A world still recovering from catastrophe. A world where ecosystems were raw, unstable, and often brutal. And that catastrophe was one of the worst in the history of life. At the end of the Permian period, around 252 million years ago, Earth suffered the most devastating mass extinction ever known. It was so severe that it makes the asteroid impact that killed the Nonavian dinosaurs look almost restrained by comparison. Around 90% of marine species disappeared. On land, entire ecosystems collapsed. Forest systems were shattered. Food chains broke. Lineages that had ruled for millions of years vanished. The biosphere itself came close to a level of collapse almost difficult to describe without sounding exaggerated. And yet, it is real. The world of Pangaea is inseparable from this extinction event. Because the supercontinent did not exist in isolation from disaster. In many ways, it formed part of the environmental stage on which that disaster unfolded. Earth at this time was already under stress. Continents had assembled. Ocean circulation patterns were different. Climate zones had shifted. The planet's chemistry and energy balance were vulnerable. Then came one of the most immense volcanic episodes ever identified, the eruptions that created the Siberian traps. These eruptions were not ordinary volcanoes in the way people imagine a cone exploding in the distance. They were flood basalt's catastrophic outpourings of magma on a continental scale. Lava flooded across huge regions. Greenhouse gases surged into the atmosphere. Carbon dioxide and possibly methane accumulated. Oceans acidified. Oxygen levels in some marine environments collapsed. Temperatures rose. Ecosystems already stressed by Earth's configuration were pushed past the point of recovery. And Pangaea was there through all of it. So when you imagine this supercontinent, don't imagine a clean, stable, prehistoric paradise. Imagine a world that had just been through hell. A giant continent scarred by climatic extremes and biological collapse. A planet trying to rebuild itself. That is what makes this period so fascinating. Because the Earth that followed was not empty. It was experimental. After the end Permian extinction, life did what it has done again and again through deep time. It adapted, mutated, spread, and occupied the ruins. The ecosystems of Pangaea in the Triassic were not yet the lush and familiar dinosaur worlds of later periods. They were harsher, stranger, and in some ways more interesting because they represent a recovery phase in planetary history, a time when the winners of the future were not yet obvious. If you were standing on Pangaea in the early Triassic, the world might have looked sparse in many regions. Forests had not fully rebounded in some places. River systems could be erratic. Drylands dominated huge areas. Temperatures in continental interiors may have reached extremes difficult to compare directly with the modern world. Some evidence suggests seasonal heat may have been intense enough to severely limit large animal activity in certain low-latitude interior zones. That matters because it changes the emotional picture of this lost Earth. Pangaea was not just one giant land bridge. It may have been one of the harshest large-scale land environments in Earth history. And yet, life kept moving. Among the survivors were synapsids, relatives of the lineage that would eventually lead to mammals. Many people imagine mammal ancestors as tiny, irrelevant creatures hiding under dinosaur feet. But in the world around the formation and peak of Pangaea, synapsids were not minor background animals. Some had already dominated terrestrial ecosystems for long stretches of time. Before the age of famous dinosaurs, The land was home to bizarre and powerful forms like Dimetrodon in earlier periods, and later to mammal-like reptiles and other synapsid groups that looked neither fully reptilian nor remotely modern in a mammalian sense. Their skulls, teeth, and postures hint at a deep evolutionary transition that was still unfolding. They were creatures of a world in between. Not the ancient world most people imagine, and not the modern one either. And that is part of what makes Pangaea feel so uncanny. It was a planet caught mid-transformation, not only geologically, but biologically. Everything was in motion. The land itself had merged into a giant whole, but life was fragmenting, recovering, diversifying, and testing new strategies for survival. Archosaurs, the broader group that would eventually include crocodilians, pterosaurs, dinosaurs, and birds, were beginning to rise. Some of the early members of that group were already showing the traits that would later make them dominant: upright movement, efficient breathing systems, and body plans suited to endurance and expansion in harsh environments. In a recovering, unstable world, those traits mattered. This is where the science becomes more than just background, because Pangaea didn't merely host life. It may have actively shaped which kinds of life could succeed. A supercontinent changes the rules of the evolutionary game. When all major landmasses are connected, migration barriers are lower in some ways. Animals and plants can spread across huge areas that would later be isolated by oceans. Groups that today would evolve separately on different continents could once disperse across connected terrain. That means lineages could move farther, interact differently, and face a broader range of climates without ever crossing an ocean. But there is a paradox hidden in that connection. Even though Pangaea physically linked land together, it did not create one uniform world. It created many worlds inside one continent. Some regions were humid, some were coastal and seasonally wet. Some were river-rich, others were inland furnace zones. Mountain belts influenced rainfall. Basins trapped sediments and water. Rift valleys opened in places long before the final breakup. High latitudes experienced very different light cycles and temperatures than equatorial belts. So while Earth's land was united, its environments were not. And that environmental diversity mattered. It created evolutionary laboratories. A creature adapted to swampy lowlands would not thrive in dune-choked arid interiors. A plant dependent on consistent rainfall would fail where monsoonal patterns collapsed or shifted. Predators evolved differently in open floodplains than they did in dense vegetated systems. Over time, this produced ecological complexity across the supercontinent complexity we only partially reconstruct from fossil fragments, trackways, pollen, bone beds, and sediment layers. That's one of the eeriest things about deep time. We know this world existed. We know it shaped everything that came after, but we can never see it directly. We are rebuilding it from clues. A footprint pressed into ancient mud, a fern spore trapped in stone, a chain of mountains now split across oceans, a desert deposit in a place that is no longer desert. And one of the strongest clues that Pangaea was real came from something so simple it almost sounds too obvious. The continents fit, not perfectly in the cartoon way of classroom globes, but convincingly enough that once you notice it, it becomes difficult to unsee. South America and Africa are the classic example, but the deeper evidence goes much farther than coastline shape. Coastlines are only the visible edges of continents. The true fit lies in the continental shelves, the submerged margins beneath modern seas. When geologists compare those deeper boundaries, the match becomes even more compelling. Then the evidence starts stacking. Rock formations of the same age and structure line up across continents, now separated by oceans. Mountain belts that seem disconnected today once formed continuous chains before the Atlantic split them apart. Fossils of the same species appear in places now thousands of kilometers apart. Not because animals crossed impossible oceans, but because those lands were once connected. This was one of the great scientific realizations in Earth history. The world map is not permanent, and once that realization took hold, everything changed. It is easy now to take plate tectonics for granted, because it is one of the central frameworks of modern geology. But there was a time when the idea that continents moved sounded absurd to many scientists. In the early 20th century, Alfred Wegener proposed continental drift after noticing the fit of continents and the distribution of fossils and geological structures. He was right about the movement, but he did not yet have the mechanism to explain how massive continents could shift. That mechanism would come later, when the seafloor itself began to reveal its secrets. Because the story of Pangaea is not just the story of continents coming together, it is also the story of oceans being born. And that is where this ancient world becomes even more dramatic. Most people think of continents as the stars of geology, but oceans are just as important, sometimes more. The floor of the modern oceans is not ancient in the same way continental crust is. Oceanic crust is constantly created and destroyed. It forms at mid-ocean ridges, spreads outward, cools, thickens, and eventually sinks back into the mantle at subduction zones. The seafloor is an active conveyor. Continents are lighter, more durable rafts riding atop a deeper engine. So when Pangaea formed, it did not simply happen because continents casually drifted into each other. It happened because older oceans closed, plates converged, subduction consumed seafloor. Continental collisions built mountain chains on scales that modern landscapes still preserve. Every time two continental blocks crashed together, Earth folded itself upward. Some of the mountains we know today are the scars of that assembly. The Appalachian Mountains in eastern North America, for example, are the worn remains of a much greater system that once linked geologically with mountain belts in what are now Greenland, the British Isles, Scandinavia, and parts of North Africa. Today, they seem separated, diminished, and fragmented. But during the assembly of Pangaea, they were pieces of a continuous tectonic drama. That alone is enough to change how you see the modern world. A mountain in one country may once have been physically connected to a mountain chain, now on the other side of an ocean. A fossil found in Brazil may have relatives in Namibia, not because of coincidence, but because the land itself was once one. A desert sandstone in the American Southwest may preserve wind systems that blew across an interior no human mind was built to intuitively grasp. This is what makes Pangaea so compelling as a YouTube documentary subject, and also so difficult to fully absorb. It was not just a strange map, it was a different operating mode for Earth, and the deeper you go into it, the more unsettling the implications become. Because once all the continents were one, Earth became a place where distance meant something different. Climate meant something different. Survival meant something different. Even the sky, depending on where you stood, may have felt different, hazed by dust, seasonally violent, or stretched above landscapes, too open and too empty to feel comfortable. And yet, that was only the beginning, because the supercontinent was not stable forever. Long before the Atlantic existed, before the familiar world began to emerge, cracks were already opening inside Pangaea itself. The giant landmass that looked unbreakable was already beginning to fail from within. And when it started to split, it didn't do it quietly. It changed the oceans, the climate, and the course of life in ways that would eventually make our world possible. The first signs of Pangaea's death did not look dramatic from a human perspective. No one would have stood on a cliff and watched a continent suddenly rip in half. What happened instead was slower, deeper, and in some ways more terrifying, because it was happening beneath the surface long before the surface made it obvious. The land was under tension. Far below the crust, heat from Earth's interior was still moving, still circulating through the mantle, still pushing and pulling on the plates above. Pangaea may have looked like the final form of the world, but geologically, it may have been too big to stay together. Supercontinents do not simply appear and then remain forever. They seem to be part of a cycle, assembling, surviving for a while, then breaking apart as the planet's internal engine keeps forcing change. And once that process begins, even a giant landmass becomes temporary. To understand what Pangaea was actually like at its peak, you have to imagine not just a single landmass, but a continent that distorted the planet's atmosphere and hydrology on a colossal scale. Because the biggest consequence of all that connected land was not simply where the mountains were or how animals moved, it was water. Or more specifically, where water could no longer reach. One of the strongest scientific reconstructions of Pangaea points toward a world dominated by climatic extremes. Its coasts would still have supported wetter systems in many places, especially where monsoonal circulation and proximity to the sea brought regular moisture inland. But the farther you moved toward the interior, the more the continent began to behave like a planetary-scale heat trap. During the day, giant expanses of land absorb solar energy efficiently. At night, they release it quickly. Water buffers temperature swings, but dry continental interiors do not. That means a place can become punishingly hot under the sun and cool sharply after dark. On a supercontinent, those contrasts can become amplified across huge distances. And because moisture from the ocean cannot easily penetrate infinitely far inland, rainfall patterns become uneven and in some places deeply unreliable. This is why ancient rocks from the Pangaean world preserve evidence of immense arid belts. Some of the most famous examples come from Triassic and Permian redbeds, thick sequences of oxidized sediments that often indicate dry to seasonally dry environments. These rocks are found across what are now North America, Europe, Africa, and elsewhere, telling a story of broad landscapes shaped by heat, seasonal runoff, evaporation, and dust. In some regions, dunes migrated across terrain that today is forest, farmland, or mountain country. In others, ephemeral rivers may have flooded violently and then vanished into dry basins. Lakes expanded and shrank. Salt deposits accumulated where water evaporated faster than it could be replenished. The climate did not have to be uniformly dead to feel unforgiving. In fact, some of the most dangerous environments on Earth are not sterile at all. They are just unstable. And Pangaea appears to have been full of instability. One of the most fascinating features scientists infer for this world is the possibility of extreme monsoonal systems. A supercontinent creates enormous thermal contrasts between land and ocean. During warm seasons, land heats up faster than the surrounding sea, drawing in moist air. During cooler periods, the circulation can reverse. On a continent the size of Pangaea, those seasonal pressure differences may have driven giant atmospheric circulation systems, creating intense wet-dry cycles in some regions. That means parts of Pangaea may have lived between two moods. One season, brutal heat and desiccation. Another, violent storms and sudden flooding. And that combination is powerful because it does not just shape weather. It shapes landscapes, ecosystems, and evolutionary pressure. A creature living in a stable, moist forest evolves differently than one surviving in a place where water arrives in pulses. Temperatures swing hard, and open terrain offers little refuge. This is one reason the Triassic world often feels more severe than the later, dinosaur-rich images popular culture tends to favor. It was a world where life was not simply flourishing under warm skies. It was negotiating with a recovering and often hostile planet. And if you were dropped into the middle of it, one of the first things that might strike you is how empty some parts of it could feel. Not lifeless, just enormous. The interior of Pangaea may have included landscapes where the horizon carried almost no sign of ocean influence, where dust traveled far, where vegetation thinned, where river channels wandered across broad floodplains and then disappeared into dry basins. In other regions, there would have been lush corridors, seasonal wetlands, conifer forests, fern-dominated vegetation, and river systems that served as lifelines across harsher ground. This contrast is important because ancient Earth was not a single visual style. It was a mosaic. That is what makes it real. If all we had was one giant swamp with giant reptiles, the story would be less interesting and less believable. But the actual Earth was more complex than that. It was compartmentalized by climate, topography, water access, and latitude. The equatorial regions behaved differently than the poles. Mountain belts interrupted wind and rain. Rift zones began opening long before complete continental breakup. Interior basins captured local environments with their own chemical and sedimentary signatures. And inside this giant shifting patchwork, life was diversifying into forms that would define the future. By the Triassic, the world was becoming a proving ground. This was the era when the line between the old rulers of the land and the future rulers had not yet fully settled. Synapsids were still present, some of them highly successful. But archosaurs were expanding. These were the broader reptilian relatives that would eventually include crocodilians, pterosaurs, non-avian dinosaurs, and birds. And in the environmental context of Pangaea, they were entering a world that rewarded mobility, efficiency, and adaptability. That does not mean dinosaurs instantly appeared as giant apex icons. Far from it. Early dinosaurs were relatively modest creatures compared with the giants that would come later. In the late Triassic, they were part of a larger ecological caste, not yet the uncontested stars of the land. Many were small to medium-sized, bipedal, fast-moving animals occupying niches in ecosystems still shared with crocodiline archosaurs, large amphibians, and other strange survivors of earlier evolutionary experiments. That is one of the most underrated facts about this world. Pangaea was not yet the Earth of Tyrannosaurus or Triceratops. It was the Earth where the stage was being built, and because all the continents were still connected, that stage was unusually open. One of the biggest consequences of supercontinent life is that animals can disperse across connected land corridors in ways impossible on a fragmented globe. Today, oceans are powerful barriers. They isolate species. They allow lineages to evolve separately over long stretches of time. But on Pangaea, terrestrial organisms could, in many cases, move much more freely between regions that would later be split apart. That is why fossils of related organisms appear across continents that now seem impossibly distant from each other. Take the famous case of Mesosaurus, a small aquatic reptile whose fossils are found in both South America and Southern Africa. It was not an ocean-crossing creature built for vast saltwater migrations. Its distribution makes much more sense if those regions were once connected. The same logic applies to plants like Glossopteris, a seed fern found across southern continents, including what are now South America, Africa, India, Antarctica, and Australia. To a modern observer, those distributions look scattered. To a Pangaean Earth, they were local. That is one of the deepest mind-bending parts of this story. Places we instinctively think of as separate were once neighbors. Modern Brazil and Western Africa were once part of the same broader, connected terrain. Antarctica, now associated almost entirely with ice and isolation, was once integrated into living continental systems that supported forests in much older geological intervals. India was not always a subcontinental projectile. It was once part of a southern continental assembly before beginning one of the most famous migrations in tectonic history. Everything moved, and because it moved slowly, it is easy to forget how dramatic the cumulative effect becomes. That movement also helps explain why some of the strangest clues to Pangaea are not fossils, but rocks that record climate. For example, glacial deposits found across NAS-abraded southern continents provide evidence that large parts of Gondwana, southern component of the larger Pangaean world, were once affected by ancient ice sheets during earlier phases of assembly. When these deposits are mapped and reconstructed, they align in ways that make sense on a joined continent, but not on the modern globe. Scratches left by glaciers, called striations, point to movement patterns that become coherent once the continents are put back together. That means even ice itself became a clue, not just where life was, but where cold once ruled. And that matters because one of the easiest mistakes to make about ancient Earth is assuming it was always hotter, always swampier, always more uniformly tropical than today. In reality, Earth's deep history includes dramatic climate shifts, including greenhouse worlds, icehouse intervals, transitions, collapses, and combinations that do not map neatly onto the present. Pangaea existed through important climate transitions, and depending on exactly when you stand within its timeline, the world around you would feel very different. At some moments, parts of it were dry and punishing. At others, wetter and more vegetated. At some latitudes, seasonal darkness and cold still shaped life in ways that challenged the stereotype of a permanently warm prehistoric Earth. And through all of this, the geography itself was setting traps for the future. Because once a supercontinent exists, it creates conditions that may eventually help destroy it. A continent that large acts like a thermal blanket over the mantle. It changes the insulation between Earth's interior and surface. Heat flow patterns may reorganize beneath it. Stresses build. The crust can begin to stretch. Upwelling material from deeper below can weaken sections of the lithosphere. Over immense spans of time, the supercontinent may begin to dome, crack, and rift. That is how worlds begin to split. At first, the signs might be subtle on a planetary timescale: extension in the crust, faulting, localized volcanic activity, basins beginning to form. Then the stretching becomes more serious. Valleys open. The crust thins. Magma exploits the fractures. Lava erupts. Sediments accumulate in long troughs. If the process continues, a new ocean can be born. That is not science fiction. That is how the Atlantic began. The ocean that now separates the Americas from Europe and Africa did not always exist. It had to start somewhere, and its birth was part of the breakup of Pangaea. Try to picture that for a second. The Atlantic Ocean, one of the defining features of the modern world, began as a wound. Not a blue basin, a crack, a failed-looking fracture that kept widening until it changed global geography forever. When continental crust stretches enough, it eventually tears apart. New oceanic crust forms in the gap. seafloor spreading begins. What starts as a rift valley can become a narrow sea, and what begins as a narrow sea can become a full ocean basin. Over millions of years, coastlines drift apart, sediment piles along margins, marine ecosystems invade, and what was once one landscape becomes two. This is not just theory inferred from map shapes. The Atlantic preserves a tectonic memory of its own birth. The seafloor records symmetrical magnetic stripe bands of rock that captured Earth's magnetic field as magma cooled at mid-ocean ridges. These patterns provided some of the most powerful evidence for seafloor spreading, and, by extension, plate tectonics itself. In other words, the modern ocean floor carries the signature of Pangaea's destruction. That is how intimate this story is. The world map we live with every day is literally the afterimage of that breakup. And when that breakup started, it did not merely redraw coastlines, it began transforming climate on a planetary scale. As continents separate, ocean gateways open. Water can move in new ways. Currents reorganize. Moisture transport changes. Coastal influence expands into areas that were once deep interior. Rainfall patterns shift. Deserts move or disappear. New mountain systems rise in different collision zones as old ones erode. Sea level interactions with continental margins change. Entire ecosystems gain or lose corridors of migration. A world of one giant landmass becomes a world of edges, and edges are biologically explosive. Coastlines create habitat complexity. Shallow seas support rich marine ecosystems. Isolated landmasses foster separate evolutionary pathways. Break a supercontinent apart, and you do not simply get more water between places. You get more opportunities for life to become different. This is one reason the breakup of Pangaea is so important to the history of biodiversity. Isolation drives divergence. A lineage cut off on one landmass may evolve in a direction its relatives elsewhere never do. Predators, herbivores, plants, insects, and marine organisms all respond to fragmentation in their own ways. What had once been a connected terrestrial arena becomes a set of partially separated evolutionary experiments. The modern biological world is built on that fragmentation. Without it, the Earth we know would not exist. But before the breakup was complete, there was a long and eerie transitional phase where Pangaea was still one world and already falling apart at the same time. That transitional Earth may be one of the most visually compelling versions of the planet that ever existed. Imagine giant interior deserts still dominating parts of the landmass, while elsewhere long rift valleys begin opening through ancient crust. Volcanism intensifies. Lakes fill faulted basins. Rivers change course. Some coastlines remain impossibly far away, while other regions are beginning to feel the first hints of new marine influence. The world would not look like a clean before and after. It would look unstable. And instability is where nature becomes most interesting. Because it was during this kind of changing Earth that the dinosaurs began to gain real ground. They did not simply appear because they were better in some simplistic sense. They emerged into a world that had been emptied, stressed, and repeatedly reshaped. They were part of a broader ecological reshuffling after mass extinction, climatic volatility, and tectonic transformation. Their rise is tied not just to anatomy, but to timing. And timing on Earth is everything. A lineage can exist for millions of years in relative obscurity, then suddenly flourish because the world around it changes in exactly the right way. That is what happened over and over in deep time. And Pangaea was one of the greatest arenas for that process ever known. Some of the animals roaming this world were deeply strange by modern standards. Giant amphibians still occupied watery habitats in places. Crocodile-line archosaurs explored ecological roles that later crocodilians would never fully replicate. Early pterosaurs took to the skies. Primitive dinosaurs moved through landscapes where they were not yet the dominant icons of prehistory, but increasingly part of the future. The Earth itself was selecting, not consciously, not with purpose, but through climate, geography, catastrophe, and opportunity. That is the hidden power of Pangaea. It was not just a backdrop. It was an active force in determining what kind of planet would come next. And perhaps the most unsettling thing about it is this. If you had lived there, you probably would not have known you were standing in the middle of one of the most important transitions in Earth history. To any creature alive at the time, the world would simply be the world. The deserts would feel permanent. The river valleys would feel ancient. The mountain belts would feel immovable. The climate would feel like reality itself. And yet beneath all of it, the crust was opening. The future was already tearing through the present. That is the scale of deep time. The planet changes so slowly that the beings living through it cannot perceive the transformation until millions of years later, when their descendants inherit a completely different Earth. And by the time Pangaea's fragmentation accelerated, the consequences were becoming impossible to reverse. New oceans were beginning to open, new coastlines were being born, and the age of one Earth was ending. But the breakup of Pangaea did not happen in a neat straight line, and the world it created was not instantly recognizable. Some pieces separated early, others stayed connected longer. Some collisions that shaped the future had not happened yet. And in the middle of all of that, one of the most important things of all was still unfolding. The planet was preparing the conditions for the world of giant dinosaurs, changing oceans, isolated continents, and ultimately, the Earth that would one day produce us. And that final transformation is where the story becomes even bigger than the supercontinent itself. Because Pangaea did not just vanish. Its ghost is still running the planet now. That ghost is everywhere. It is in the curve of South America, facing Africa like two broken edges of the same ancient body. It is in mountain systems that only make full sense once the Atlantic is erased. It is in fossils found on opposite sides of oceans that did not yet exist when those organisms were alive. It is in deserts that formed where the climate once behaved according to a continent so large that it no longer has a modern equivalent. Pangaea is gone. But the world you know is built from its collapse. And once you see that, modern Earth stops looking finished. It starts looking like a snapshot. This is one of the most important mental shifts in all of geology. We are not living on the final arrangement of the planet. We are living inside a temporary phase of a machine that has been reorganizing itself for billions of years. The continents on your map are not destinations. They are positions. That changes everything. Because when Pangaea began to break apart, it was not simply creating distance between landmasses. It was creating the physical conditions that would define the next 200 million years of life, climate, ocean circulation, and evolution. The breakup was not a single event. It unfolded in stages, and each stage altered the planet in ways that rippled outward through time. One of the earliest major divisions separated Pangaea into two enormous pieces, Laurasia to the north, and Gondwana to the south. Laurasia included what would become North America, Europe, and much of Asia. Gondwana included South America, Africa, Antarctica, Australia, India, and other southern fragments. Even that split alone is hard to fully visualize, because it was not just a line on a map. It was a reorganization of coastlines, basins, climates, and migration routes across a planetary scale. And then the fragmentation continued. The Central Atlantic began to open. North America and Africa started pulling apart. South America would eventually separate from Africa as the South Atlantic opened later. India broke away and began its astonishing northward journey across the ocean. Australia and Antarctica remained linked for a long time before parting. The Tethys Ocean, once a major marine realm between continental blocks, evolved and narrowed as collisions reshaped Eurasia. The pieces did not all drift at the same speed or in the same direction. Some rotated, some collided again. Some carried entire ecosystems into new climatic zones. The map of Earth was not merely changing, it was becoming biologically and climatically more complex. And this is where the story becomes much bigger than the continents used to be together. Because once the supercontinent fragmented, the planet's circulatory system changed. Modern Earth is heavily controlled by ocean currents. These currents move heat around the globe, influencing storms, rainfall, temperature, and habitability. The Gulf Stream, the Southern Ocean circulation, the exchange between basins, these are not small details. They are some of the hidden architecture of the modern climate system. But ocean currents depend on geography. Open or close a seaway, and you can redirect planetary energy. Shift a continent, and you can change where warm water travels, where cold water upwells, where marine nutrients circulate, and where moisture reaches land. That means the breakup of Pangaea was not just about continents drifting apart. It was about Earth rewiring itself. As new oceans widened and new coastlines formed, marine habitats expanded. Shallow continental shelves became biologically rich environments. Isolation increased. Evolution accelerated along separate pathways. On land, continental fragmentation created barriers and opportunities that would shape dinosaurs, mammals, flowering plants, insects, and eventually entire modern ecosystems. This is the part of the story that often gets lost when people think of Pangaea as just a cool prehistoric map. It was not a curiosity, it was a hinge point. The modern world is a consequence of its destruction. Without that breakup, the history of life would almost certainly have unfolded differently. The rise of dinosaurs as global giants, the later isolation of lineages on separate continents, the distinct faunas of South America, Africa, Australia, and North America, the future migration routes of mammals, the marine systems that later fed whales and sharks, and endless pelagic life, all of it sits downstream from tectonic rearrangements that began when Pangaea started to fail. Even some of the world's most dramatic future events were made possible by those movements. India, for example, was once attached to Gondwana, but after breaking away, it became one of the fastest moving major continental blocks in geological history. For tens of millions of years, it raced northward across the Tethys Ocean before slamming into Asia. That collision did not merely stop India, it helped build the Himalayas. And the Himalayas are not just mountains, they are climate engines. Their uplift influenced monsoons, erosion, atmospheric chemistry, and long-term environmental change across huge parts of the planet. A tectonic story that begins in the breakup of a supercontinent eventually helps create one of the most powerful geographic systems on modern Earth. That is how deep these consequences go. Or take the opening of the South Atlantic. Today, South America and Africa are separated by ocean, but they were once joined. Their eventual separation changed ocean pathways, altered atmospheric circulation, and isolated lineages that would continue evolving independently. What now looks obvious on a globe is actually the result of a very long and violent geological uncoupling, and Antarctica perhaps one of the strangest examples of all. Today, it is the coldest, driest, windiest continent on Earth. A frozen fortress of ice and katabatic winds, isolated by the Southern Ocean and wrapped in one of the most powerful ocean current systems on the planet. But Antarctica did not always live this way. Its isolation was built. When Antarctica finally became more fully separated from surrounding landmasses, and ocean circulation around it intensified. Especially with the development of the Antarctic circumpolar current, the continent became increasingly thermally isolated. That isolation helped lock it into deep cold over geological time. In other words, one of the most alien-looking places on modern Earth is part of the afterlife of continental breakup. And that should tell you something extraordinary. Some of the most extreme environments on the planet today are not just random. They are inherited. Inherited from collisions, separations, uplifts, openings, and closures that began long before humans existed. This is why geology can feel almost unsettling once you really absorb it. The world around us is not just scenery. It is history made physical. The ground beneath your city, the mountains on the horizon, the fossils in museum drawers, the oil trapped in sedimentary basins, the metals concentrated in ancient crust, the shape of coastlines, the pathways of storms, none of it is accidental. Earth is a memory machine, and Pangaea is one of its biggest memories. But maybe the most astonishing part of all is that Pangaea was not unique. It was not the first supercontinent, and it almost certainly will not be the last. That idea changes the emotional scale of this story completely. Because if Pangaea was one chapter in a repeating tectonic cycle, then what we think of as the natural world is really a temporary arrangement between much larger acts of planetary reassembly. Before Pangaea, there were older supercontinents, including Rodinia, and probably others even deeper in Earth's past, assembled and broken apart under tectonic regimes that are harder to reconstruct the farther back we go. And if plate tectonics continues as every line of evidence suggests it will, then Earth's continents are still moving toward futures we will never see. The Atlantic Ocean, which was born from the breakup of Pangaea, will not remain open forever on geological timescales. Oceans can close. Subduction can consume seafloor. Continents can collide again. Mountain chains can rise where there are now coastlines. New supercontinents may eventually form under entirely different configurations. Some reconstructions and models propose possible future supercontinents with names like Amasya, Pangaea, Proxima, or Novo Pangaea, depending on how the plates continue moving over hundreds of millions of years. The exact outcome is uncertain, because the deeper future of tectonics is difficult to model with precision over such immense spans of time. But the principle is clear. Earth is not done rearranging itself. The world map is temporary. That alone is enough to make the modern planet feel strange again, because the oceans that seem permanent are young in deep time. The continents that feel eternal are wandering. The mountains that look immovable are decaying. The climate patterns we build civilizations around are nested inside a system that has reinvented itself again and again. And that brings the story back to the original question. What was Earth like when all the continents were one? It was not simply a giant version of the world we know. It was a harsher, stranger, more unified, and in some ways more unstable Earth. A world of immense continental interiors, extreme climate contrasts, recovering ecosystems, ancient deserts, emerging dynasties of life, and tectonic tensions already preparing the next collapse. It was a planet where distance worked differently, weather worked differently, and the future was still hidden inside the crust. It was a world before the Atlantic, before modern coastlines, before the continents became familiar, before Earth learned to look the way we expect it to. And maybe that is the most powerful part of the whole story. Pangaea reminds us that normal Earth is an illusion. The map in your head is not the truth of the planet. It is only the current frame in a film that has been running for billions of years. We tend to think of oceans, continents, and climates as the stable background of life, but deep time reveals the opposite. Life is adapting on top of a world that never truly stops moving. The continents drift, the oceans open, the mountains rise, the climates shift, the dominant creatures vanish, and Earth keeps going. That should be humbling, because for all our roads, borders, cities, and satellites, we still live on a surface shaped by forces so old and so large that human history barely registers against them. Entire empires have risen and disappeared in less time than it takes some coastlines to noticeably move. Our species has never seen a supercontinent. We evolved on the fragments. We are children of the breakup. Everything we call the modern world, our migrations, our climates, our ecosystems, our isolated continents, even the evolutionary paths that eventually made human existence possible, was shaped by the death of one giant landmass. And if that sounds unreal, that is only because the real history of Earth is almost always stranger than fiction. There was once a time when you could have crossed much of the planet without crossing an ocean. A time when the world was one, and the evidence is still beneath your feet. If you want more real stories about the strangest eras, places, and forces this planet has ever produced, subscribe to the channel, like the video, and tell me in the comments which lost Earth you want to explore next, because the deeper you go into this planet's past, the less normal it becomes.